Okay, good morning, everybody. My speakers didn't seem to plug in properly. Nope, they're playing silly buggers. Okay. Hope nobody needs to talk to me because they're on, but they're just in the really stupid mode. No, don't share Dropbox folder. So last class we talked about the introductory stuff to the course. We covered the syllabus. We talked big picture about some of the concepts we're going to be talking about. This class, we dive right into content, I guess. So I'm going to start today with discussing a bit about carbohydrate structure, some key terminology we're going to be using, and then looking at how, the basic idea of why carbohydrates are so interesting, especially when they're in solution, and what's going on there and how we can make use of their unique chemistry to do things with them. So if we're thinking about carbohydrates, the name is right, like what they are is right in the name. They are the hydrate of carbon. And this is because we knew the molecular formula of these things before we knew anything about their structure or anything about that, because the first thing we had as an analytical tool was ways to measure molecular formulas. So what is a hydrate of carbon? Well, that's carbon. And a hydrate of carbon is, well, I add water. So almost all the standard carbohydrates have that molecular formula. Like you multiply them by N, and N is often 6 for like glucose and mannose and galactose and stuff. But it's that. So that's where the name comes from, and that's what they are. Another way I think about these is these are ridiculously hydroxylated molecules. For some reason my pen's taking a moment to update on my screen, which is really weird. It's better, I think. Oh. So my handwriting is probably going to be even worse than normal. So when we're thinking about this, I am just going to draw beta D glucose. Again, you don't need to memorize the structures of any of these things. You can look them up. So this is called beta D glucopyranose. You'd also call it beta D glucose. It is also known as D-glucose. So why are there so many effing names for the same thing? Well, it's because this is not a stable molecule. You put this into water, it does not stay like this. So we're going to pull apart what all these thingies mean. So I always click too quickly and I screw this up. So I'll try not to. The D part refers to the stereochemistry at C5. Why? We'll talk about that in a moment, maybe later this class, maybe next class. But if that is that stereochemistry, it's a D sugar. All the natural sugars are D sugars. Every sugar that we use generally are D sugars. There are L sugars out there, which are the enantiomer of that. Mostly used in weird-ass bacteria and archaea. But eukaryotes all use D sugars because life is chiral and it's arbitrary. The beta part comes because the stereochemistry of this center is the opposite of the stereochemistry of the D center. And again, we're going to see how that's the case because it's not clear why it's the opposite. They're both up. What the hell is going on? Chemistry is weird. But effectively, we're referring to the relative positioning of that. The gluco part discusses the relative stereochemistry of all the carbons on that site. So the fact that this, not except for this one, except for, I'm going to change color. Except for this one, the first one. Gluco refers to the relative stereochemistry of these 4 carbons. If they were different, you would have a different name for the sugar. It would be a different sugar. Again, because that first carbon there that I've highlighted in blue can be either, and still be the same molecule, because they interconvert, and we're going to see how, that doesn't change whether it's glucose or not. But the other 4 all need to be the same relative to each other for this to be glucose. If we, just as a quick cheat, in glucose, everything is equatorial. That makes it a little bit easier to recognize glucose. The pyranose thing refers to the fact that this is a 6-membered ring. So beta D glucopyranose tells me that I have a D sugar. This carbon 1 thingy here. Damn it, I should not have done that. Damn it, I should not have done that. The carbon 1 thingy here is equatorial or opposite, even though it's equatorial. The carbon 5 thingy. The gluco tells me the relative stereochemistry of every single one of the atoms, and the pyranose tells me it's a 6-membered ring. So that's what the name tells me. Now, the reason this all gets complicated is because if I put this into water, I get a mix of things. This interconverts to this guy. This is the alpha. Everything else is the same. It's still D-glucopyranose. It interconverts to this guy. Notice it's a 5-membered ring now, and suddenly we have a carbon chain dangling off the side here. So this is alpha D, still glucose, because we haven't changed any stereochemistry, although fool me if you realize that. I always have to remember which way this goes. I'm leaving this, it is, I'm drawing, it's glucose, trust me. I just can't remember off the top of my head if it's back or forwards, and I just don't want to take the time to do that right now. And it's called a furanose. This interconverts, they all interconvert, I'm just drawing arrows like this, to, well, if we can get an alpha furanose, it shouldn't surprise that we can get a beta furanose. And we're still not done. There's a 5th one. And it's kind of the tricky one that you don't think about. It's the open chain form, which is responsible for everything going wrong. I'm going to draw it like a semi-pure nose here. And this is the open chain. And we would just call this glucopyranose or glucose, D-glucose. Because it's still D, we haven't changed any of the stereochemistry, but we don't know if it's alpha or beta because it's an open chain because the ring's not closed. Yeah. So there's 5 different forms that coexist in solution. If I take the sugar, put sugar in solution, all 5 of these forms are present. So how is this happening? We call this thing mutarotation for how these interchange. So let's look at that. So if I have for those of us at home, which I guess is all of us, that's alpha because it's axial there at the C1 position. It's still glucose because everything else is equatorial. It's still pyranose because there's it's a 6-membered ring. If I put this into water, whenever you're drawing mechanism, something's got to happen. And I would say, 80% of all organic mechanisms begin the same way, which is you protonate something or you deprotonate something. You add a hydrogen or you take a hydrogen off. It's just how all chemistry proceeds. So let's add a hydrogen. And for the sake of argument, and because it will shortcut our conversation, I'm going to add a hydrogen to the ring oxygen. Why the ring oxygen? It can add anywhere else. If it just adds anywhere else, nothing interesting happens. But if we add to the ring oxygen, something interesting happens. So we do that. Let's see what happens. That doesn't look all that interesting. And I promised interesting. Well, interesting for carbohydrates. We protonated an oxygen. That's just turned it into a decent leaving group. So we're going to get cleavage of that C1 oxygen bond. And look what we've made. We've made the open chain version of the sugar. So it's open chain now, right? We've broken that bond. We've generated a protonated aldehyde. Sugars are aldehydes. We never see them that way because whenever you have an aldehyde that can make a 5 or 6-membered ring with an alcohol, it ring closes almost all the time. And so that's why we always see the sugar as a 5 or 6-membered ring. We think of it that way. If you think of sugars, which you might not because you might be normal. But I always think of sugars as 5 or 6-membered rings, normally 6-membered rings because 5-membered rings upset me. And I don't think of them as an aldehyde, but sugars are aldehydes. They're constantly forming the aldehyde when they're in solution. And so they actually react like aldehydes. You can do all kind of aldehyde chemistry on sugars and it works just fine. Anyways, we've made this. So now we have some options. If we just go straight backwards using the principle of microscopic reversibility, which basically says anything you can do forward, you can do backward just the same, we go straight back to where we were. That is not particularly interesting. More interesting thing that can happen is we do a rotation. It's not really an equilibrium because no reaction's happening. So I'm going to use my made-up arrow that I always use for rotation. It just means I rotated something. And what am I going to rotate? I'm going to rotate the C1 position. So suddenly the aldehyde is now going to be equatorial instead of axial. Nothing else changes. Because I just rotated around that bond. Okay, and still positively charged. I'm bad at this. Okay, well, if we were able to open an aldehyde when that thing was vertical, we can close the aldehyde when it's equatorial. Nothing is stopping us do that, so let's do that. And again, equilibrium arrows, everything is in equilibrium. And now we've gone to the beta. Cool. Okay, well, okay, not that cool. What if we do another type of rotation? So here what we're doing is we're making the 6-membered ring. But if you remember your second year organic chemistry, is there a ring size to form that's faster than 6? This is the audience participation portion of the course.
Six always form faster.
Sorry, which size forms faster, Ronas?
6.
Nope, 6 does not form faster.
It's not. It's
Not
6
the
is more
fastest.
stable.
Yes, but that doesn't make it the fastest.
Oh.
And that's great. I'm really glad you just pointed that out because we're going to talk kinetics versus thermodynamics, which I think is one of my favorite subjects after resonance. Hazel.
5-membered ring.
5. 5 is the fastest ring size in the history of ring sizes. 5-membered rings always form fastest because you're at the right balance of again, going back to second year organic chemistry, which I'm sure all of you have taken some time. It might have been a long time ago for some of you. 5-membered rings always form faster because you have the right mix of strain on the bonds, on the angles, and things are real close, and close things bang into each other more easily. So 5 is the fastest. 4, there's too much strain on a ring. 6, things are a little bit further apart, even though all the bonds are perfectly relaxed, which is unique for 6. So 5 is about 10 times faster than 6 to form. So we just drawn 6s, but we can do 5, and we can get to 5 by going, well, I want to close onto the aldehyde with an alcohol, and I count 1, 2, 3, 4, 5 atoms, that oxygen. So that oxygen currently is nowhere near that aldehyde, so I'm going to have to do a little bit of work, and I can do that by rotating this bond. And if I do that, no, okay, I guess I'll draw it in green because it's easier to draw it in green than to change the color of my pen. So if we're just keeping track of where atoms have moved, this guy here was this guy here. And this guy here was this guy here. So we just rotated a bond, moved things around, and suddenly we're setting ourselves up for a 5-membered ring closing. Let's close the 5-membered ring, snap her shut. Everything is in equilibrium again because everything is always in equilibrium. and we kind of get the envelope confirmation that you may or may not remember for 5-membered rings. And if you don't, that's okay, because it's not really that important, because we're not really going to spend any time talking about 5-membered rings, because I find them awkward, and I think the pedagogical benefit is limited, except in this thing, just make sure that you're aware that this happens. 5-membered rings are the dominant form for smaller sugars. So the sugars we're talking about so far, like glucose is called a hexose. It's got 6 carbons, hex, ose, 6, sugar. Ribose is a pentose. It's got 5 carbons, pent, 5, ose, sugar. And although there's nothing stopping ribose making a 6-membered ring, it seems to prefer 5-membered rings. And I'm sure there's a perfectly good thermodynamical argument for it. I just don't know it. I think it's got to do with steric clashes of the non-existent C6 chain. But I haven't crunched the numbers ever, so I don't want to say that's the case because I don't know. But 5-membered rings are not important for hexoses, and I'm mostly interested in hexoses because I don't care about nucleic acids. And we can get the final thing we need by rotating this bond. Oh, by the way, this is the alpha furanose, right? So we rotate that. Oh, look, it's equatorial. Guess I could have left this as an exercise for the listener or the ones who are going to watch this on recording, I hope. I magically added an extra carbon. I noticed I hadn't uploaded the lecture slides from last class. I will do that today after this class, and I'll upload these as well. The videos are up on YouTube if you need to find them. I think it's my YouTube channel. If you type my name into YouTube, you'll find it. But I'll make sure I add a link to the syllabus, and I'll update the syllabus as well, to the YouTube playlist. Anyways. And you can find my old lectures from last year also up there, but I think I'm reorganizing them a bit this year because there's going to be a little less chemistry and a little more things that aren't chemistry this year because of the audience. Unless all that's left in this room is chemists, and then in which case this becomes more chemistry again. But I'm honestly not trying to scare people off. Just teaching a course I think you guys should all have as biochemists or chemists. Anyways, beta furanose. So we got alpha furanose, we got beta furanose, we got alpha furanose, we got beta furanose, we got the open chain. And I've drawn the open chain this way. And to be honest, that's the way I prefer to draw open chains. But the world doesn't agree with me. The world wants to draw that open chain using a dumbass convention invented by a brilliant man, and it's his only major mistake. And I still can't forgive him for it. And so what we'll often do is, what's my next slide? No, I don't want to use that. Okay, I'm going to put it down here. It's called a Fisher projection. We are going to be using them a little bit more in the next bit. These were invented by M.L. Fisher, who basically invented everything. I'm really glad he's dead, because if he wasn't dead, I wouldn't have a job. None of us would. We'd all just be Fisher's postdocs forever. He was so much smarter. Like, he made the first sugar, he made the first nucleic acid, he made the first peptide. He identified the structure of sugars. He identified the fact that carbon is tetrahedral. Just, it's embarrassing. So this is called a Fisher projection. It's a projection of glucose. What this means, again, we teach this in second year. I teach it very grudgingly because I hate this projection. What it means is that if I look at any given carbon, so if I'm looking at that carbon, for instance, I'll change my color of my ink so it's a little bit clearer. What I'm seeing is hydrogen I haven't drawn on the left coming out towards me, the OH on the right coming out towards me, the aldehyde above going out away from me, and the chain below going out away from me. That is, I find that really hard to visualize. It's kind of like, well, I actually have a model kit here and I have a camera and we are doing this remotely. And so nothing is stopping me from just going through what a Fisher projection of a sugar looks like. So, there, my mouse is working, great, okay. So if you have a ring thingy, you know, I got 5 atoms here, I don't have 6, whatever. Normally when we draw a line, like a ring, a line, as an organic chemist, we do it as a zigzag formation. Like that's what we're used to drawing. Fisher projections are not that. Fisher projections are everything is in a ring. And what you do is you look on each atom identically. So you look at it like this. So you're looking directly at the atom. The top and bottom go away from you. The left and right come towards you. And then the next atom down the chain, what you're doing is you're not kind of looking at this angle. You have to actually change your perspective, rotate the entire ring, and now look at it head on. Again, left and right are coming directly towards you. Top and bottom are going directly away from you. Next atom, you need to rotate the ring again, do that again. This is pretty hard because what we're kind of doing is we're looking almost, a Fisher projection is almost a 4-dimensional representation of a 3-dimensional object because we're looking at it in 4 dimensions such that this has all like been turned into a straight line. And we can look at the 3-dimensionality of it that way. And it's very, very confusing because we're not 4-dimensional creatures, spatial dimensional creatures. Because that's silly. But when Fisher came up with the Fisher projection, we didn't know how matter was organized. So for all we knew, this made perfect sense. People use it. I think it still gets asked questions on the MCAT, and that's about it. I'm going to use it for one thing in this course only, and it's to discuss the proof of the stereochemistry of sugars. And I may or may not get to that because I love it, but it's really not all that important. So this is called mutarotation, and this is what happens whenever you have an OH group at that C1 position. And the word has slipped out of my mouth a few times. So I want to make sure I define it here. We call this position the anomeric position. Why is it called the anomeric position? I don't know. No idea. I would then call this molecule here and this molecule here anomers of each other. You could say they are diastereomers of each other. That is also completely correct. But they're interchangeable diastereomers in that they flip back and forth between each other. So yeah, they're diastereomers, but diastereomers are often like stable, and these guys aren't. So are they diastereomers? Well, yes, but they're kind of like a special subclass of diastereomers because they can interchange, but they don't necessarily interchange. You can crystallize out one or the other. And then if it's not in an OH there, then they are actually stable, and then they're clearly diastereomers, but they're also anomers. I'm going to tend to use the term anomer when I'm talking about diastereomers at C1. The other term that I will use is the term epimer. Epimer means you have swapped some but not all of the stereocenters at a given site. So these two molecules are epimeric at C1. It's kind of a more general term than anomer because it can be for any molecule. And saying that they're the same molecule except C1, the stereochemistry is different. So that's the term epimer. So alpha, beta are epimers. So I'm going to use the term epimers and anomers, and I just know I'll try and avoid using epimers because it's not all that relevant, but I know I will use it because I'm thinking about other things when I'm lecturing, like I'm kind of thinking about what to do next and all that, so I'm not choosing my words as carefully. So I know it'll slip out, so I want to make sure you've seen it too. Okay, that's the terminology I think we need right now. So what I want to get into next is I just showed you all these things and these mutarotations. So what does this matter? Well, let's take a look at the equilibrium ratios of these guys. So we're going to look at a few of my favorite sugars. So glucose, galactose. Galactose is my favorite sugar. Mannose, ultrose. Ultrose is my least favorite sugar. I am completely just there's no real reason for that. Galactose I have a loving relationship with, a love-hate relationship. It's actually kind of Stockholm syndrome. But ultrose is just there's no reason for the hatred. I've never worked with ultrose. I just dislike how it looks. I find it upsetting and confusing, and I don't want it to exist. And methyl glucoside. And so what I mean by that, what the hell is a methyl glucoside? It's glucose with an OMe group, a methyl group at the anomeric position. So that OH has a methyl group instead of just a, what's the word I'm looking for? Instead of just an OH, it's the methoxy group. The last thing I'm going to add on here is I'm going to add cyclohexanol. In this case, it's not going to be epimers we're going to be talking about or anomers. It's just going to be a ring flip from equatorial to axial for that OH. Anyways, so alpha pyranose, beta pyranose, alpha furanose, beta furanose. Open chain. Well, part of this table is really easy to do. 0, 0, 0, 0, 0, 0. So, and for the methyl glucoside, it can't mutarotate because there's no OH at the anomeric position. Again, what am I talking about with that? It's because I just realized that I'm using words instead of pictures, and I should use pictures because pictures are better. Anyways, there's a methoxy group there. And I've just drawn the alpha, but let's say the beta. So this is equilibrium reaction. Everything else is the mutarotation in water. Okay. So let's start with cyclohexanol. Let's just think about that. Sorry, cyclohexanol, John. Cyclohexanol, John. So all we got is cyclohexanol, nothing else there. There's a single OH, it's a cyclohexane ring, and it can ring flip because chairs ring flip because that's what chairs do. Because geometry hates you. Qualitatively, I don't need numbers because if any of you actually has this number, that would blow me away. I don't expect you to, but qualitatively, which of those is predominant? Or are there equal amounts of those in solution? I take cyclohexanol, I throw it in solution, and I take my little magic molecular camera, and I can take pictures of all the molecules and I can count them. Are more of them going to be the axial one on the left or the equatorial one on the right? I'm patient. I have a lot of coffee to drink.
Is it about anomeric effect here?
No, not yet. This isn't going to be the Anomeric effect. This is just standard sterics. This is going to be Anomeric effect we're going to be talking about. Yeah, absolutely, Hazel. That's where we're going. But right now, just cyclohexanol, there is no anomeric effect. It is just sterics. I'm basically asking, do substituents prefer to be alpha or axial or equatorial on a ring?
Oh, equatorial.
Yeah, of course. They prefer to be equatorial by about 5 to 1. So an OH group prefers to be equatorial by a ratio of about 5 to 1. So if we're looking at that, the beta pyranose form of cyclohexanol is 80-20. Sorry, that's 4 to 1. I'm not good at math, so let's just say 85-15 and call it even. It's somewhere in between 80-20 and 85-15. I don't know, sure. There. Put an about sign on it, get myself out of trouble. And actually, these are non-applicable because it's not a 5-membered ring, so it's not going to be that. So, on pure steric arguments, groups don't want to be axial because of steric and 1,3 diaxial clashing, right? You remember your 1,3 diaxial clashing. If you don't know what 1,3 diaxial clashes are, I can recommend some really, really good basic organic chemistry textbooks. If you need an E fundamental organic chemistry textbook and you're taking this course, please let me know and I can arrange to make sure you have a very good one. Happy to provide that. So again, the only difference between an alpha pyranose and a beta pyranose is the stereochemistry at the anomeric position. Is it axial or equatorial? So everything else is the same. So yeah, of course we expect some divergence from this number because, you know, chemistry, everything's different. But roughly speaking, we'd expect a 5 to 1 ratio of beta to alpha because that is the only difference, and that is going to drive the energies, is the sterics. And sterics drive it 5 to 1 in favor of the beta. Well, it's not what we see. For glucose, it's 64 to 35 to 0.1 to 0.1. Well, shit, it really doesn't like the pyranoses. It does like the beta pyranose the most. That's good. But it likes the, but that's not 82-18. That's like half as good. Galactose is 29 to 64 to 3 to 4. So suddenly there's a lot more of those pyranoses around. Galactose, for anyone who wants to know, as I said, it's my favorite sugar. You will probably develop a favorite sugar too. I'm drawing this as a wiggly line because I'm not saying whether it's alpha or beta. But notice that the C4 position is now axial in galactose. That is the only difference. It is nowhere near this site, but that messed everything up. Now we really changed the alpha and beta pyranose ratios, and we've decreased the alpha ratio. Mannose says, screw you to rules of stereochemistry, and basically completely inverts the glucose values. Now it prefers the alpha to the beta, which is just insane because it's saying, I want steric clashing, give me steric clashing. I want an axial anomeric position, which sterically clashes with stuff. ultros, sorry. Ultros is over here. I'll just show the structure. Again, squiggly line at the anomeric position because I'm not defining if it's alpha or beta, because we have both here. This is why I hate it. I just don't like the C3 axial. It upsets me. Suddenly has an awful lot of the furans, like tons of them. Talos is kind of like if galactose and mannose have a baby. Sorry, I draw this at an angle and I'm going to make my life hell. Again, the only difference between all these sugars, right, is notice the C6 position never changes. Because if the C6 position changes, we switch to being an L sugar. We're no longer a D sugar. So what we're changing is we're saying changing the stereochemistry of 2, 3, and 4 relative to each other. That's Talos. So the C4 and the C2 are axial. Mannose, the C2 is axial, but I think a lot of you might know the structure of mannose. Anyways, there's no pattern here, right? Like you can stare at this and try and figure it out. But there's no clear pattern in here. But what is really clear is that this is of limited explanatory potential. The only difference between the alpha and beta pyranose for all of these is the orientation of the anomeric substituent. And that should be 5-to-1 favoring the equatorial. And it is clearly not 5-to-1 favoring the equatorial. And just to fuck us up, we're saying, okay, well, all these things can interconvert all the time. Weird things are happening. Let's look at the methyl glucoside. So what you do is you take glucose, you heat the crap out of it, and methanol with some acid, and you get the ratios of the products at equilibrium. Everything's in equilibrium. The alpha methoxide, glucose, the beta methoxide, they all interconverting in between them. You get the eventual product ratio, and it's mostly alpha. So at equilibrium, it wants OME axial, not equatorial, but it should want it equatorial at a 5-to-1 ratio, but it has OME axial at a 2-to-1 ratio. So this doesn't make sense. This is energetically impossible. And so initially, we considered it was magic. So that's just odd. Like there's this magical effect that was just said to be, well, you know, we don't really understand what's going on here. But there's obviously something special about sugars and something special about life, and these ratios are different. And of course, these ratios were not the first things that people ever did when they figured out sugars, because they can measure the different ratios of these guys. I think I actually talked about everything I want to talk about on this slide on that previous slide. But let's just do one quick thing. If we look at, just need to find my right note. Not my right note. Oh, come on. Just had this. I have like a whole lot of notes scattered all over my desk right now. And so, and by desk, I mean over my laptop. There we go. Okay. So let's think about what we actually expect. So as I said just now, acid, methanol, we got a 2-to-1 ratio. But if I take just the cyclohexane version of this, I don't think everyone's ever made the fully substituted version, like with all the hydroxyl groups in place to compare. And suddenly I want to do that and try and actually measure this directly. But anyways, problem for another day. This is 3-to-1. So with the OH, it was 5-to-1. That was bigger. Now we're down to 3-to-1. But what we're seeing when we have all this other stuff in here and we have an oxygen in a ring is it's 2-to-1 the wrong way. We're favoring the more hindered, sterically hindered one by a factor of 2. Whereas we expect to favor the less sterically hindered one by a factor of 3 because that makes sense and that's how the world should work. So we can take this ratio and we turn this thing into something called an A value. And the A value of any substituent is kind of a how much space does it take up? How much size does it take up? How much does it force something to go equatorial in a cyclohexane ring, which seems really, really specific. So it equals the equilibrium constant of concentration at the equatorial over the concentration axial. So what we can do then is we can actually do a few different things with this. So if we take sorry, I'm just trying to figure out my exact thoughts on this. No, this is good. Okay. We can actually take this and we can measure delta G's from this. So, who cares? I don't really care about this. There's something going on. We can do some math, but it doesn't matter. There's something going on here. It's weird. What's going on? We call this effect the anomeric effect. I have all these notes where I've scribbled out how to do the delta G calculations and measuring the different energies of these things, and I just realized I just don't care. This isn't a math course. It doesn't matter. But we have, because what matters is you have this difference. And so the anomeric effect is compensating for this huge difference. And so how does that work? Well, there's 3 explanations for the anomeric effect. One is a dipole repulsion explanation. Two is a charge repulsion, which is similar. and 3 is a stereoelectronic argument. So we're going to walk through all 3 of these together. I'm on team 3, but I grudgingly admit that there are cases where the events in number 1 and number 2 seem to actually play a major role, and it's very grudging because I don't want them to be important. And so I'm framing my biases here. I think explanations 1 and 2 are bullshit, except the thing is they work, so they're not bullshit. But I think it's mostly about number 3. Anyways, so if we think about number 1, it's talking about dipoles. Okay, so let's just take a look at what we're seeing here. So we're going to simplify our sugar down to just the anomeric center and the oxygen next. So we're not going to worry about anything else on the sugar because it doesn't matter that much. So let's just draw 2 sugars. Okay. Let's think about the dipoles now. So both of these oxygens have 2 lone pairs. I'm going to indicate the lone pairs by drawing them in sp2 orbitals. Sorry, that's pretty messy, even for me. The convention I'm using here is the same as sort of the wedge and hash convention for that you see. So a darkened lobe is coming out towards us. A dotted lobe is going back into the page away from us. So if we draw that, we have where the lone pairs are on our 2 oxygens. Okay, I want you to sketch the dipole moments for both of those oxygens, for both the alpha and beta form. So draw in where you think the lobes should be for the alpha sugar. I haven't drawn them on the 2 oxygens, but where the lone pair should be. And then draw the atomic dipole. So where the dipole is right on the oxygen itself. Don't worry about the molecule as a whole, just the atom. And remember, dipoles are vectors. So they're going from the more positive end of the atom to the more negative end of the atom. I'll give you guys a few minutes or seconds. Okay, hope dipoles are drawn. So hopefully you had no trouble putting the lone pairs on this guy. If you did, I am seriously concerned because it's exactly the same as the other guy. And again, these rely on the whole idea that these are sp3 hybridized atoms, so they are all tetrahedral. So once you figure out that, hey, these 2 bonds are in the plane, it means that the remaining 2 orbitals, one must be coming out of the plane towards me. One must be going back into the plane away from me, because that's how tetrahedra work. So those are where those are. Those are the orbitals. Now, if we draw the dipole, the negative part is where the electrons are. So we're going to cut directly between, just made a real slashing motion with my arm, between the 2 electrons clouds. And so that's going to be where the negative thing. So if we're drawing the dipole here, it is going from positive inside the ring to bisecting where the lone pairs are. And similar, we have that. Whereas over here, it's the same because it's the same. And we have that. Now, these are the 2 dominant dipoles in the molecule because these are the most polarized atoms because they're oxygen. Everything else is carbon. Carbon is boring as dirt, except because carbon's really important, so it's really not boring. But, you know, dipole-wise, it's pretty boring. And if what we're noting here is dipoles are aligned, dipoles are opposed. So, which of these is better? If you're a molecule, think like a molecule. Embrace your inner molecule. Which would you prefer to be? One with your dipoles aligned or one with your dipoles opposed? In the interest of exploration and public shaming, Michael, do you have an idea on that? I'm just gonna start calling people out.
Honestly, I'm not too sure.
Okay. So when you're trying to get an overall dipole of a molecule, you add the two dipoles together. So roughly speaking, the overall dipole for this guy is going to be kind of like that, whereas the overall one for this one, you can add the two vectors together, is going to be tiny like that, kind of.
So when they're opposing, they cancel each other.
Right. So do you want to cancel dipoles or do you want to make your dipole bigger? Which one sounds more stable?
Wouldn't canceling each other make it more stable?
Absolutely. Perfect. Because a big dipole means you have a lot of charge separation. It means your positive side is really far away from your negative side, and we don't like that. We like it when there is no charge, right? All the charges cancel each other out. And so you want to cancel your dipole. Perfect. See, you did know. So, yeah, what we're trying to do is and so what I've done to get these lines, I've added the two vectors together. I just drew them, tip to video on. Drew them tip to tail, kind of like that. Like here's one vector, here's another vector, and then I just draw the hypotenuse, and that gives me the overall vector. And in the opposed one, they kind of almost cancel each other out, so the hypotenuse is really, really short. It's not really a hypotenuse anymore. I don't know what you call it. It's the other bit of the triangle thingy. I'm not good at geometry. So we want to cancel dipoles. We want to eliminate dipoles. We want dipoles not to exist. So smaller dipole, overall dipole. Equals more stable. Alpha wins. So that's good. Now this is cool and all, but there's absolutely zero evidence. So what's really interesting that does support this is strong dipoles are stabilized in polar solvents. This is just a universal rule. It also makes perfect sense. If you have a big dipole, it means you're polar. Like that's literally what the words mean. You have charge separation within the molecule. You have a negative side and a positive side. And if your solvent is polar, it can better accommodate something that is polar. If your solvent is nonpolar, it doesn't accommodate something that is polar. Anomeric effect is stronger in nonpolar solvents. So if the anomeric effect was stronger in polar solvents, that would tell us that the dipoles don't matter. Or that something else is going on altogether. But the fact that the anomeric effect is stronger in nonpolar solvents, and nonpolar solvents can't accommodate dipoles, they want to minimize dipoles, and we see a stronger anomeric effect in that, it seems to make sense that, hey, minimizing dipoles seems like a good idea. It seems to play into designing the anomeric effect. So I don't want this to be true. I don't want this to be important because it seems like a really stupid explanation for me. I feel like whenever anyone starts referring to dipoles as an argument, it's kind of like when you start calling your enemies Nazis to win an argument. Like, yeah, they might be Nazis these days. This analogy, 5 years ago there were no Nazis. Now there are Nazis everywhere. But calling your enemies Nazis kind of, used to win you an argument. Now there are probably people who are very happy to be Nazis. So, I always think when you're kind of falling back on you run out of arguments at that point. I think with dipoles, I always feel like you've run out of arguments. It's like, oh, okay, this one again. You have no other better argument. The problem is it happens to be true, and this upsets me, but I don't make the rules. So that's one explanation. The second explanation is charge repulsion, which is similar but different. So okay, I'm really sick of oxygen. So let's think about where the electrons are on this thing. Crudely speaking, the electrons are forming a cloud around the oxygen and bromine. You can actually draw in the orbitals that we just did and use those if you like, or if you don't believe in hybridized orbitals, and you want to think about this in terms of unified molecular orbitals over the entire molecule, be my guest. I don't think of it that way. It's true, but I can't do it. You're going to have increased electron density around the oxygen and the bromine. And electrons don't like being near other electrons. In beta, they're close. In alpha, they're far. And the anomeric effect is stronger the more electron withdrawing. The anomeric substituent is. So, bromine is pretty electron withdrawing. Carbon is not very electron withdrawing. If I had a carbon there, you have a very weak anomeric effect. If you have a bromine there, or fluorine, God forbid, you have a very strong anomeric effect. Fluorine is actually ridiculously strong anomeric effect. So the more electron withdrawing that thing is, the higher the electron density is around that substituent, and the more it gets repulsed away from the oxygen's electron density, because the two big clouds of electrons don't want to be near each other. Like, this is just sterics 101. Other big electron clouds don't want to be near other big electron clouds. I also hate this argument. It's true. It works well There are a few holes with it, which we'll come across in a bit, but it definitely plays into the overall anomeric effect. The third thing, and the one I really believe in, is the stereoelectronic effect. So how many of you who has heard the term stereoelectronic before? Nobody has ever heard the term stereoelectronic.
I've heard it before, but it's been a long
Sweet.
lockdown.
Okay, but you've heard it. That I think that still puts you in a group of one.
All right.
Seriously, Hazel and Ronas? Okay. I'm a bad professor.
Stereoelective? Yeah.
Electronic. Yeah? No?
Stereoelective means based on the stereo selectivity.
It's based on both sterics and electronics.
Yeah.
The
Of course.
the big joke in chemistry and synthetic chemistry is if I'm asked how something works and I don't know, I always say it is a delicate balance between steric and electronic effects. Because, so, okay, let's take apart those words. We kind of started this in the first class. When I talk about steric effects, what am I talking about?
Hindrance clash. Atoms getting in each other's way.
Clash. Okay, I like what you're saying there with atoms getting in each other's way. Let's take a closer look at that. What part of the atoms are getting in each other's way?
Electrons?
Right.
Because it must be the surface of them, so electrons.
Perfect. Electron cloud battles. Electrons hate electrons, right? So if I've got a lot of electrons around me and something else has a lot of electrons around them, and we're getting close to each other, we're going to sterically repulse each other because we're going to try and put our electrons in the same place, and they don't want to be in the same place because they're all negatively charged and everything's banging into everything else, and then we push each other away in disgust. That's sterics. So electrons clashing through space. What are electronics? Not like at the molecule level, like not your cell phone or my tablet, which I just dropped. It's okay. I have a Persian carpet underneath my desk, and I just about dropped it again. This is electron density in a bond on an atom. I think these are kind of the ways to think about them. Sterics is where we're talking about relationships that occur because electron clouds are interacting with each other through three-dimensional space, not through bonds, through three-dimensional space. Whereas electronics are where we're talking about electrons interacting with atoms and with each other through bonds. And so where the electrons are preferring to sit to minimize charge separation. So stereoelectronics is when we are minimizing charge separation through space. So the two are kind of smudged together in a smudgy mix. So you've seen these arguments before, I hope. Let's take the E2 elimination. If you don't remember what the E2 elimination is, it's I take something like bromoethane. I treat that with a strong base. I don't know, sodium hydride. I like sodium hydride. And I get ethene. The mechanism is base attacks hydrogen, electrons in a hydrogen carbon bond create a new double bond, electrons in a carbon bromine bond break, and I get the product. I get hydrogen gas and I get Br minus. So, okay, there are no stereoelectronics here at all yet. Is there anything that we need to know about the relative orientation of the hydrogen and bromine for this to work? Does it matter how they're oriented?
I don't think it does, but I'm not sure.
It does matter how they're oriented. It's very, very important. So if we're thinking about that, I don't know if any of you remember the term, maybe, you know, digging deep in the memory palace.
And the E2 is on T.
Antiperiplanar?
It should be opposite of the living group.
Right.
The way the nucleophile attack and living group should be in opposite direction.
Perfect. They need to be opposite each other. They need to be antiperiplanar to each other. And that's because this is a stereoelectronic argument. There's no reason to justify that any other way. Like if I just draw arrows like that, man, it doesn't matter where that's positioned. You can draw the arrow, it's fine. But it's because chemistry doesn't happen through like simple arrows. So they need to be antiperiplanar to each other, and that's because it's a stereoelectronic argument. What we have is, let's just take a look at a really simple version of this. All I'm doing is I'm drawing the bromine. Again, this is this molecule here, and I'm only worrying about the carbon bromine bond and one of the carbon hydrogen bonds. I've abstracted everything else because they don't matter. This is a molecular orbital. It is a sigma orbital. There are electrons in it. I'm drawing, you know, there. If you remember your sp3 orbitals, there's a little nubbin, a lobe at the other side. There's a big lobe facing the atom, and there's a little lobe facing the other thing. But for every bonding orbital, there's an antibonding orbital. There's a sigma star. The antibonding orbital forms when when the orbitals forming the bond are out of phase. And normally it's out of phase for the weakest bond. The weakest bond in this molecule is the carbon bromine bond. You can look up the bond dissociation energies if you don't believe me. Let's not, because Nobody wants to look up bond association energies. They are out of phase. This nubbin is dark. It's positive wave function. This nubbin is bright. It's a negative wave function, or vice versa. Nobody cares. Those aren't charges. They're just signs of the wave function. And I know this sounds kind of complicated. I'm literally teaching the introductory organic chemistry class right now to second-year students, and they are already asking me tons of questions about molecular orbital theory and in-phase and out-of-phase bonds on class number 1. So apparently we went there a little sooner than I was expecting. So this is the first class ever of organic chemistry talks about this stuff. So if you can't remember this, please just bone up a little bit on basic molecular orbital theory. But it's an antibonding orbital because there is no electron density between a carbon and bromine. And so if any electrons go in to occupy that orbital, it's negative energy. We're going to break the bond. So, cool, it exists. It's just empty. So it's purely theoretical that it exists. Like, it doesn't matter for the molecule because it is an empty orbital. There are no electrons in it, so there's no energy in that orbital. So it doesn't matter the orbital exists. But the orbital does exist because, of course, it exists. And try not to think about it too hard because your brain will fry. Now, let's think about what happens when we bring a base into the system. H minus, 2 electrons. So it's going to try and find a place to put those electrons because it's got 2 electrons. And I'm going to be really simplistic here because it's actually a combination of molecular orbitals as the whole thing forms through a transition state and it gets really complicated. Let's not do that. Let's just say that we're going to put them into the antibonding orbital. So this has got 2 electrons and it's going to go grab this hydrogen. And by doing that, it's adding 2 electrons to this system. So it's putting those into the antibonding orbital. So let's use a different color. So this is, and I'll draw them like that. And so as it adds the electrons and does the deprotonation, it adds 2 electrons to the antibonding orbital. As soon as we added electrons to an antibonding orbital and there's electrons in a bonding orbital, you break the bond. That is what happens when you add electrons to antibonding orbitals, is you break chemical bonds. Cool. Now, the only reason this works, and let's think about this for a second, is because as the electrons in this one go, well, suddenly that's adding 2 electrons to this. We're going to release the electrons in the carbon-hydrogen bond. There's 2 of them there. They're not going onto the hydrogen, they're going to go onto the carbon. So we're going to have carbon with 2 electrons. And they need to find somewhere to go. Because right now, what I've just made there is C minus. And C minus sucks. I am never going to make C minus. So if what I actually make is 2 electrons stuck on that carbon, there's no fucking way that that reaction is going forward. That is an impossible reaction. It is never going to accept those electrons because it doesn't have anywhere to put them. They are massively unstable. This is just physically impossible. Luckily for us, there's somewhere to put them. So if you remember, if we take a look at what the molecular orbital for ethene looks like, there's sigma, it's occupied. There's sigma star, it's unoccupied. Notice that the bonds are out of phase. These can't interact with each other. These can't interact with each other because they are out of phase, whereas here they're in phase, everything's good. Doesn't matter, it's unoccupied. But what I want you to look at is this occupied thing. You've got a p orbital adjacent to a p orbital. Well, if we look at the antibonding orbital up here, and we think about the electrons being stuck in here, you know, that big juicy lobe over there looks an awful lot like a p orbital. Whee! So we jump our electrons into that, and suddenly we are sharing electrons between two big orbitals. We are breaking away the bromine, and we are becoming the ethene, because those sp orbitals rehybridize, become p orbitals, and we lose the bromine. This is only possible because this lobe here is perfectly lined up with this lobe here. If they are not lined up, these electrons are stuck and they can't go into this orbital. So if the hydrogen making this not anti-periplanar, no reaction. If the hydrogen is not directly opposite the bromine, you can't get the reaction to go because the electrons have got nowhere to go, because the electrons are trying to interact with an orbital and they're not lined up, so they can't go there because they're not lined up, and it's really frustrating. So this is a stereoelectronic effect. We are talking about arrangement in three-dimensional space, and we are talking about electronics. We are talking about where the electrons are going. So literally stereoelectronics. It is 9:54. Class ends at 10. Class ends at 9:50 for the academic hour. I think before I start the next discussion on the stereoelectronic effect relative to the anomeric effect, which will take some time, I don't want to get 6 minutes in and have to call it a day. So I'm going to stop here for today. The video is going up on YouTube. The notes are going to go up on Blackboard. So I think we're good. Any questions about this besides what the fuck just happened? Strongly recommend that if your response to this is what the fuck just happened, I strongly recommend that you email me. I can send you a textbook, fundamental organic chemistry textbook, or you start doing a little bit of reading on stereoelectronic effect on Wikipedia. You can look it up on Khan Academy, like the intro organic tutorial thing. They've got some stuff on there too. We're going to be having to think a lot about the arrangement of orbitals in space. This goes into carbohydrates, this goes into amino acids, this goes into degradable polymers. All this stuff really relies on degradation driven by orbital arrangement in space. And there's really no other way to explain it, except by not explaining and just saying it happens this way. But I never want to teach that way. So it's complicated, but it's not that complicated. Take some time to bone up on this. I'm going to send out 2 papers. It is Wednesday. We don't meet again until Monday for you guys to read. One is a translation and summary of M.L. Fisher's determination of the stereochemistry of the carbohydrates. The second one is a review article on the anomeric effect. I'm going to pick a short one of those. And I think that, or maybe I'll send you 2 review articles on the anomeric effect, and they disagree with one another because we still don't know what the fuck is going on, really. So if you come out reading those 2 articles and you're still kind of confused because you're seeing these arguments and you don't know which one's right, that's an awesome feeling. I don't know which one's right. I have a bias, but I don't know. And on the Fisher one, there's a question on one of the assignments about trying to think about this in terms of the way M.L. Fisher would have thought about that to determine something else. It's one of the best logical proofs ever. Math always likes its logical proofs, and the mathematicians and their proofs, they all get excited about their proofs. And I envy them because it's true. Like, it's just true in a true way. There's not a lot of chemistry proofs, but this is a chemistry proof where you just use pure logic to figure something out, and it's beautiful. And beauty is beautiful. So it's worth working through, and the paper is pretty good. So yeah, that's what I'm going to send out. Take a look at those for Monday. We're going to be working more on the anomeric effect. The reason I'm sending you those papers is because questions on the assignments that go into the exams take stuff from those papers, and so I'm spoon feeding you the material here. You just need to think about it a bit, and I'm happy to answer questions on it and talk about it, but you do need to do the reading and the thinking. Okay. That's all I've got.
Thank you.
You're welcome. Have a good rest of your day. Stop recording.